In early 2023, astronomers using the Atlas survey in Hawaii detected a faint, fast-moving patch of light against the stars. At first it looked like an ordinary outer solar system comet, but follow-up observations changed that view. Orbital calculations showed the object was on a hyperbolic trajectory, the hallmark of an interstellar visitor, and by mid-2023 the Minor Planet Center had confirmed it. Designated 3I/Atlas, this was the third recorded object ever proven to come from beyond our solar system. Almost every subsequent observation deepened the mystery instead of resolving it. 3I/Atlas is unusually large for a detected interstellar object. Brightness and dynamical models place its minimum diameter at several kilometers, and mass estimates derived from measured non-gravitational accelerations imply a density far higher than typical cometary ice and dust. Its orbit is both unusually flat and precisely timed. Its incoming path lies within a few degrees of the ecliptic plane where the planets orbit, and the timing of its passage lines up to allow close approaches to Mars, Venus, and Jupiter in sequence. Those two facts together are statistically unlikely for a randomly arriving interstellar body. Spectroscopy and polarimetry added more surprises. Observations across multiple facilities found the coma dominated by carbon dioxide rather than water vapor, and several independent spectra reported a nickel-rich signature where iron would normally dominate. Polarimetric measurements showed extreme negative polarization values not normally seen in cometary dust. High-resolution imaging captured an elongated, forward-directed jet of scattered light, a beam-like structure pointing toward the Sun instead of the familiar tail that is blown away from the Sun. This forward jet persisted over months, and the conventional models for cometary activity do not easily reproduce its morphology or stability. All of this came together just before an international observation campaign timed for October 3, 2025, when 3I/Atlas made its closest approach to Mars. Multiple orbiters and a suite of ground and space-based telescopes were positioned to capture the event. The Mars Reconnaissance Orbiter with its high-resolution camera, ESA's Mars Express with optical and infrared instruments, ExoMars, and other orbiters with spectrometers, NASA's MAVEN with ultraviolet spectroscopy, and contributions from other national missions. Those teams expected unique, high-value data, images that could resolve the nucleus size, spectra to test the unusual chemistry, polarimetry to characterize the dust, and time series observations to measure any non-gravitational accelerations precisely. Instead of a coordinated public release, the space agencies have been largely silent. Months after the Mars encounter, no major data dump, press release, or preliminary image set appeared from NASA or ESA. That gap in public reporting is notable because agencies typically publicize rare successes quickly. Mission teams often release preliminary images and spectra while detailed analysis continues. The absence of immediate transparency fueled intense speculation in the scientific community and the public. There are plausible mundane reasons for delayed publication: technical issues in spacecraft pointing or data transmission, extended time needed for careful calibration and reduction of faint signals, or complex international review protocols for cross-agency data sharing. But the pattern of anomalies, size and density inconsistent with ordinary cometary composition, the forward jet, the nickel-rich spectra, the polarization signatures, and the orbital timing, combined with the lack of prompt public data, has pushed some leading scientists to ask harder questions. A minority of respected researchers have argued that the combined evidence merits serious consideration of non-natural explanations, while most of the community urges exhaustive tests of natural models first. The critical test points are clear and imminent. Infrared observations with powerful space telescopes could reveal whether there is an internal heat source. Continuous radio monitoring by SETI and large radio observatories could detect narrowband or structured emissions. High-resolution optical and infrared imaging near perihelion could reveal surface structures or confirm a natural, irregular nucleus. And rigorous, transparent publication of Mars orbiter data would allow the global research community to validate or refute anomalous claims quickly. How those data are handled, whether released openly or reviewed in closed channels, will shape not only the scientific verdict but public trust and the policy response. This is more than a technical puzzle. If the object is explainable as an extreme but natural outcome of planetary formation and interstellar dynamics, it will expand our understanding of what nature can produce. If the object resists natural explanations even after independent verification, the implications become profound. Evidence of engineered materials or directed behavior would force a rethinking of search strategies for extraterrestrial technology, international coordination on data and disclosure, and the cultural framing of humanity's place in the cosmos. The discovery of 3I/Atlas has already moved the conversation from speculation to a set of concrete, testable predictions and to urgent questions about how science, policy, and the public should respond. Researchers distilled 7 core anomalies that separate 3I/Atlas from previously observed interstellar visitors and from typical solar system comets. Each anomaly is described below with the observational basis, why it challenges standard models, and the leading natural and non-natural interpretations scientists are testing. 1. Size and implied mass. Observations and inference, photometry, modeling of brightness evolution, and analyses of non-gravitational accelerations were combined to estimate nucleus size and mass. The most conservative models place the minimum diameter at several kilometers, while dynamical constraints imply a mass that is orders of magnitude larger than what typical cometary composition would suggest for that size. Why this is anomalous? Comets of comparable visible size in our solar system are far less massive because they are porous aggregates of ice and dust. An object with that brightness but far higher mass implies either an unusually high density or substantial hidden mass. Natural explanations under consideration: a fragment from a differentiated planetary core, an unusually compact composition, metallic or highly processed material, or systematic errors in the non-gravitational acceleration models. Non-natural interpretation: a dense engineered structure or heavily shielded probe with mass concentrated in a compact volume. 2. Orbital inclination and timing alignment with planetary encounters. Observations and inference: the incoming trajectory displays a low inclination relative to the ecliptic, only a few degrees, and orbital geometry timed the passage to allow close approaches to Mars, Venus, and Jupiter. Independent orbital solutions from multiple teams reproduce the geometry. Why this is anomalous? Interstellar velocity vectors are expected to be distributed widely. Prior interstellar objects arrived from very different inclinations. The combined coincidence of low inclination plus optimal timing for multiple planetary encounters is unlikely under naive random arrival models. Natural explanations under consideration: observational selection effects. We are more likely to detect objects crossing the ecliptic, or a parent population with kinematics favoring low inclinations. Non-natural interpretation: a plotted trajectory selected to maximize scientific encounters, i.e., mission-style planning. 3. Forward-directed jet morphology. Observations and inference: high-resolution imaging in optical wavelengths revealed a narrow, elongated beam or jet of scattered light oriented sunward, forward along the direction of motion, rather than the canonical anti-sunward tail. The jet persisted with stable orientation over months. Why this is anomalous? Solar radiation and solar wind normally produce tails blown away from the sun. Jets pointing toward the sun and remaining stable are not reproduced by standard sublimation and rotation models. Natural explanations under consideration: a persistent vent geometry combined with a specific rotation axis, sublimation dynamics of exotic volatiles producing directed flow, projection effects. Non-natural interpretation: directed emission consistent with propulsion or controlled mass ejection. 4. A coma chemistry dominated by carbon dioxide and unusually high nickel relative to iron. Observations and inference: spectroscopic surveys across facilities detected CO2 as the dominant volatile in the coma while water vapor was weak or absent. Several independent teams measured emission lines suggesting an elevated nickel signal compared to iron. Why this is anomalous? Most comets, including distant ones, contain abundant water and show iron dominance or typical cosmic abundance ratios. Nickel-rich outgassing is atypical and reminiscent of engineered alloys if taken at face value. Natural explanations under consideration: formation in an extremely cold, CO2-rich environment, origin as a fragment of a differentiated body, core material, or supernova-enriched region, measurement or calibration artifacts. Non-natural interpretation: ablation or corrosion products from metallic surfaces or engineered alloys. 5. Extreme negative polarization signatures. Observations and inference: polarimetric measurements showed a degree and sign of polarization unusual for cometary dust at similar phase angles, with values more consistent with large or highly reflective particles or with metallic grain populations. Why this is anomalous? Typical comet dust yields positive polarization in the observed regimes. The negative polarization here implies different grain size distributions, shapes, or refractive indices. Natural explanations under consideration: unusually large grain sizes, coated grains, or mineralogies with exotic refractive properties. Non-natural interpretation: engineered coatings, layered composites, or metallic particulates released from a hull. 6. Timing that enables multi-planet flybys. Observations and inference, orbital geometry and epoch prove that the object's path allows encounters with several planets at times when observational campaigns were active or could be scheduled. Why this is anomalous: achieving sequential close passages without active trajectory adjustments from a random interstellar arrival is statistically unlikely. Natural explanations under consideration, serendipity and a posteriori selection biases in detection and reporting. Non-natural interpretation, planned reconnaissance path through the inner system. 7. Directional alignment with the historical WOW signal region. Observations and inference, the arrival direction aligns within observational uncertainties with the general sky region associated with the 1977 WOW radio spike. Statistical treatments vary, but the apparent coincidence drew attention. Why this is anomalous: the WOW signal remains unexplained, alignment could be coincidence, but layered with other anomalies, it raises curiosity. Natural explanations under consideration, chance alignment and the fact that many directions on the sky are plausible, the original WOW location uncertainty is large. Non-natural interpretation, a common origin region for radio emissions and the object or an ancient beacon/launch site. Synthesis and scientific posture. Individually, each anomaly may be explained by alternative natural models or by measurement uncertainties. Together, however, they form a cluster that is statistically unusual and scientifically interesting. Responsible science demands both rigorous attempts to find natural physical and chemical models that can reproduce the data and open consideration of alternative hypotheses where warranted by independent reproducibility, falsifiable predictions, and transparency of raw datasets. The coming observation windows and the perihelion passage will be decisive in narrowing possible interpretations. Framing the debate. Scientific norms: science proceeds from null hypotheses grounded in prior knowledge. Extraordinary claims require extraordinary evidence. The community therefore treats non-natural explanations cautiously and demands thorough testing and independent reproducibility. Problem statement: the cluster of anomalies in 3I/Atlas strains conventional models. Researchers must evaluate whether a single natural model can plausibly reproduce all observables or whether invoking an engineered origin is a less contrived hypothesis. Leading natural hypotheses and their strengths/weaknesses. 1. Fragment of a differentiated body or planetary core. Strengths: can account for high metal content and density if the object is a fragment of an iron-nickel core ejected by a violent collision. Differential fractionation could explain unusual elemental ratios. Weaknesses: requires an ejection mechanism capable of populating interstellar space with such fragments. Core fragments might not produce comet-like Comet unless heavily processed or coated with volatiles. 2. Formation in an exotic stellar environment. Strengths: star systems with unusual nucleosynthetic histories or local supernova enrichment could yield atypical elemental abundances. CO2-rich volatiles might dominate if water was sequestered or otherwise altered. Weaknesses: such environments are rare, isotope ratios and other trace element patterns should be diagnostic and need measurement. 3. Sublimation in jet models with unusual vent geometry. Strengths: complex nucleus geometry and rotational states can yield atypical jet morphologies. Rare configurations might mimic forward-pointing features in projection. Weaknesses: persistence and stability of the forward jet over months is difficult to sustain with standard outgassing physics. 4. Measurement and selection artifacts. Strengths: spectroscopic S/N limitations, calibration errors, or line misidentification can bias composition inferences. Observational selection biases influence detection statistics. Weaknesses: multiple independent teams have reported similar anomalies, which reduces but does not eliminate the chance of shared systematic biases. Artificial probe and engineered origin hypotheses. Rationale: a dense, metallic object that outgasses nickel-rich particles, with a persistent forward jet and an optimized trajectory through the ecliptic, matches some expectations for a reconnaissance probe that uses robust materials, has mechanisms for course control or reaction mass, and targets multiple planetary encounters to maximize scientific return. Testable predictions if true. O non-gravitational accelerations inconsistent with passive outgassing models and possibly correlated with directionality indicative of thrust. O detection of narrowband, structured electromagnetic emissions or modulated optical signals inconsistent with natural processes. Thermal excess beyond solar heating that would indicate internal power generation. Surface geometries or repeating, regular structures detectable at sufficient resolution. Methodological cautions. Statistical independence. Many of the anomaly probabilities are not strictly independent. Correlations must be quantified to avoid overestimating the improbability of natural explanations. Bayesian framing. Update priors with new high-quality data. A rigorous Bayesian analysis can compare the plausibility of alternative models given the data and their respective predictive power. Replication in open data. Releasing raw observations to the community accelerates independent tests and reduces confirmation bias. Sociological context and professional risk. Historical reluctance. Researchers who previously raised artificiality hypotheses for other interstellar objects faced professional pushback. This has chilled some discussion and slowed the formal exploration of non-natural scenarios. Balanced approach. Credible scientists advocating openness stress that considering engineered hypotheses is not fringe if done with rigorous criteria, falsifiable predictions, and a roadmap for tests. What happened around October 3, 2025? Observational readiness. Multiple Mars orbiters and ground teams planned observations for the predicted flyby window. Instrument suites included high-resolution visible imaging, infrared spectrometers, ultraviolet sensors, and radio receivers, a full multi-wavelength campaign. Publicly accessible rover frames. Independent amateurs stacked Perseverance raw frames and reported a faint smudge consistent with the predicted sky position, demonstrating that something was visible from Mars surface cameras. This increased expectations that orbiters had higher resolution data. Silence from agencies. In contrast to typical practice for high-profile observations, there was no immediate coordinated public release of orbital imagery, spectra, or initial findings from NASA, ESA, or partner agencies. Possible benign explanations for delayed or absent public release. 1. Data quality and processing time. Faint signals and complex calibration requirements can delay reliable scientific products for weeks or months. 2. Coordination and embargoes. Multi-agency campaigns often use controlled data sharing protocols to respect mission priorities and collaborator agreements. 3. Technical problems. Pointing errors, data loss, or corrupted telemetry could prevent usable orbital images. Concerns fueling speculation and political interest. The pattern of anomalies plus the absence of prompt orbital data invites questions about internal interpretation debates. Reports surfaced of expedited reviews, requests for internal briefings, and heightened interest from some policy actors. Public figures referenced the issue and called for transparency. Implications of withholding. Delays without clear reasons increase distrust and encourage misinformation. Conversely, premature release of ambiguous or misinterpreted data can produce confusion and false narratives. Institutional tensions and recommended governance practices. 2. Internal cultures. A cautious camp favoring careful analysis before public statements and an open data camp that argues raw data should be released immediately for independent verification. Both positions have merit. The conflict illustrates the challenge of balancing rigorous scientific vetting with public accountability. Recommended practices. Adopt a transparent embargo system with clear timelines, provide provisional data releases with explicit caveats, enable independent teams to access raw archives under short non-disclosure windows if necessary to prevent premature media misinterpretation, but prioritize timely public release of validated datasets. Legal and political levers. Congressional oversight. Legislative bodies can demand briefings and documents. They can also create political pressure for disclosure. International checks. Partner agencies, ESA, Roscosmos, CNSA, etc., hold their own data and can counterbalance any single agency's opacity. If one partner releases data, others are likely compelled to follow. Critical near-term tests and observations. 1. Perihelion monitoring. January 13, 2026. Watch for changes in brightness, morphology, and non-gravitational accelerations. Perihelion is when thermal effects maximize and exotic behavior may become most apparent. 2. JWST and infrared observations. If approved, mid-infrared spectroscopy can detect thermal anomalies, internal heat sources, and compositional fingerprints not visible in the optical. 3. Radio SETI campaigns. Continuous monitoring for narrowband or structured emissions across radio bands and optical SETI searches for pulsed or modulated optical signals. For polarimetry and spectroscopy campaigns, repeated measurements to track changes in dust properties, grain sizes, and elemental ratios. Look for isotopic diagnostics that would support or falsify supernova enrichment or planetary core origin scenarios. 5. Transparent release and independent analysis. Full archival release of Mars orbiter datasets to enable broad verification. What would count as decisive evidence? Strong indicators of artificiality, structured, information-bearing electromagnetic emissions, repeated non-gravitational thrusts correlating with directional control, thermal excess implying active power generation, resolved geometric features inconsistent with natural rubble or irregular nucleus morphology. Strong indicators of natural origin, consistent, quantitatively modeled outgassing behavior that predicts accelerations in morphological change, compositional and isotopic patterns matching known natural processes, high-resolution imaging showing irregular, natural fracture patterns and no engineered structures. Broader scientific and societal implications under different outcomes. Confirmed natural extreme object, advances in planetary formation theory, improved models of interstellar object populations, and refined detection/characterization strategies. Confirmed artificial probe, silent fundamental shift in SETI priorities from only listening to active searches for artifacts, new emphasis on long-lived physical probes as durable evidence of past or extant civilizations, ethical and governance discussions about response and data sharing. Confirmed artificial and responsive, profound geopolitical, cultural, philosophical consequences with immediate policy questions about communication, security, and international coordination. Practical recommendations for the scientific community and policymakers. 1. Prioritize rapid, transparent data sharing with clear metadata and calibration information. 2. Fund coordinated, multi-wavelength campaigns for perihelion and post-perihelion monitoring. 3. Establish international working groups to define criteria for declaring artificiality and to advise on communication protocols. 4. Expand planetary defense and rendezvous capabilities to include tools for safe close observation and potential interception of maneuvering objects. 5. Engage social scientists, ethicists, and communicators to prepare public messaging and manage societal response. Final scientific posture and philosophical reflection. The scientific method requires us to hold hypotheses in provisional terms and to pursue tests that can disconfirm favored ideas. 3I/Atlas is a case study in how to apply that method under intense public scrutiny and political pressure. Whether the object proves to be a natural outlier or evidence of engineered artifacts, the appropriate scientific response is the same: accelerate data collection, enable independent analysis, quantify uncertainties, and design decisive tests. The story has already catalyzed a richer conversation about how humanity looks for evidence of other technologies, not only across the electromagnetic spectrum but in the material artifacts that may drift between stars.